Alright guys, so here for the second part of the double, continuing on with exponential graphs. Remember we talked about exponential growth previously, and remembering that exponential growth, if we were to look at, if we were to quickly sketch it, it's something that is getting larger and larger and larger as time goes on. And population size is a great example of exponential growth. Investments like compound interest, like we mentioned earlier, virus growth, funny enough, and they've got this last example here, the size of a bushfire can be modelled or described using exponential growth. So jumping in and looking at an example here, so example 6 goes on, the population of a seaside grows exponentially according to the function p equals 5,000 outside of 1.08 to the power of t. Before we move on, that looks, similar to compound interest or the future value formula, isn't it? It's very similar in how it's set up. And we can see that because our a value, that base value, is bigger than 1, this is, and our power, it's the power of t, so when we look at the positive values, it's going to grow. Right? And t is the number of years, and here we've got to be careful when we read this, it's the number of years after 2020, and p is the population at the start of the year. So it's the population at the beginning of the year for every year after 2020. So our first question here is, what was Seaside's population in 2020? Well, 2020 is just 0 years after, isn't it? So our power is going to be to the power of 0. 2020 is 0 years after 2020. And remember, anything to the power of 0 becomes 1. So what we're left here is 5,000 times 1. So our population is 5,000, and this is our initial population. What we're starting off with at the beginning of our model. And that initial population, that's also going to be our y-intercept if we were ever having to graph that model. Part B says, calculate the population of Seaside in the year 2026 to the nearest whole number. So if we have a look at that, well, 2026 minus 2020, so that's 6 years after 2020. So our we're going to raise it to the power of 6. When we plug that into our calculator, we're going to get 7,934.37 blah blah blah, and rounding that to the nearest whole becomes 7,934. Part C says, graph p for values of t from 0 to 10. So I've kind of started that process off, and I know at 0 I have 5,000. We know at 6 we had 7,934. We got those from the previous 2 questions. So just go through and punch those values on your calculator. I've already done that for a lot of them. So 5,400 after the first year, 5,832, 62. Feel free to fast forward to I finished this. 6,802. And 10,795. All right, and we've been asked to graph that. So this will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So down the bottom there, I'm going to have my time since. On my vertical axis, I'm going to have population in thousands. And what am I growing? I'm growing from, so let's go 2, 4, 6, 8. No, we can do better than that. Let's just go. We'll undo. 1, 2, 3. No, let's not do that. Two, 4, 6, 8, 10, 12. Oh, I've made my axis too big, but anyway, 5,000 is going to be about there. And because this is an exponential model, 5,400's somewhere here. If I let's look at that, I get over 6,000 in the third year, so 6,000 the third year is going to be about here somewhere, and then 7,000 in the fifth year, so fifth year just over 7,000. So our curve, oh, hang on, let's just put those points in to make it better. Very close to 8,000 in the sixth year. Very close to 8,000 in the sixth year, somewhere here. In the seventh year, where am I? Seventh year, I'm 8,500, so we're up here somewhere. So you can kind of see this curve. It's kind of doing this. And I don't need that part there. So we've kind of got that. The last thing to do, remember, is to label. So population equals 5,000, so I have 1.08 to the power of t. Right, hope that was okay. Again, with graphing these ones, we're not going to expect an accurate graph because it's so hard to draw an accurate non-linear graph. We're just wanting something that's got that rough shape that's looking like it should be. Question E. D says use guess and check to find when the population will triple that of 2020. So if we go to D, triple 2020, well, that's just 5,000 times 3. So we're looking for when does our population reach 15,000. And we can kind of guess. Well, we're going to use guess and check. So I'm going to use my graph to start off, and I can see that, well, using our graph initially and our table of values, I'm picking a number that's way bigger than 10. I'm probably going to go for something like 13 to start off with. So when it comes to guess and check, we want to see working out. So we want to see our guess, we want to see our result. All right. Guess and check, it's a valid method, but you need to show multiple guesses and results to actually use it as a valid method. All right. So I think the first guess I want to throw out there is I'm going to guess 15. And 15, when I throw that into our formula, is going to give us 15,861, which is too high. All right, so now I'm going to guess something that's lower. It's not too far off, and we know this is only gradually growing, so I'm going to guess the number 14. And when I guess 14, I get a result of 14,685, which is, too low. So, but the number I need, the exact number I need, is somewhere in between there. Now, if we go up to the question, it says when the population will triple that of 2020. So I'm having a look at this. It's somewhere somewhere in the year 2034. If I have to think about that, that at the beginning of 2034, it's too low. At the beginning of 2035, it's too high. So somewhere in the year 2034, the population will triple. So finish that off with a nice sentence, and remembering that I'm using 2034 because that's 14 years after 2020.